All right, we're going to go ahead and get started here. So, because we have a lot of material that we're going to cover here today, and we want to make sure we have ample time for Q&A. So, welcome. Great to see you all here today at the first installment of our Louisiana Clean Fuel webinar Wednesday series, Transportation Electrification. And this session, we'll be talking about multi-port megawatt charging systems for medium and heavy duty EVs. And this is just part one of this topic. But first, we want to start off by thanking our Clean Cities partners for their help promoting this webinar series. The Dallas-Fort Worth Clean Cities, Land of Enchantment Clean Cities, and the Arkansas Clean City Coalition. So before we introduce our panelists, I want to take a few minutes to talk about the Clean Cities program. Since transportation is such a critical aspect of our nation's energy consumption, the Department of Energy has offices that focus on how transportation relates to the DOE priorities of national security, economic growth, affordability for businesses and consumers, and reliability. So our Clean Cities program is under the VTO, which is the Vehicle Technology Office. And the VTO develops advanced transportation technologies that fit with the Department of Energy's main priorities, which is to improve energy efficiency, increase domestic energy security, reduce operating costs for consumers and businesses, and to improve global competitiveness of the US economy. So Clean Cities coalitions help the VTO achieve their goals through conducting activities in these key areas: advancing vehicle technologies, new mobility choices, idle reduction and fuel economy improvements, and alternative and renewable fuels infrastructure. Our portfolio in Clean Cities includes all the alternative fuels. As a fuel agnostic organization, you can be sure that when we help a fleet or when we help you with your decisions on technologies to adopt to reduce your emissions, that we're going to find the one that works best for you. We are not funded by any particular industry, so we are not going to be pushing one product or one solution for you. We want to make sure that you have a good experience and that you get the very best advice that you can get. So where can you find a Clean Cities Coalition? Where there's almost 100 of us across the country, as you can see here. And, no matter where you are, there's probably a Clean Cities Coalition near you. And if you don't have one in your area, you can just pick one that's nearby, and you will find that we're all very helpful and that we love to assist people with their alternative fuel and emissions reductions projects. And if you're encountering a challenge, it's very likely that there's another Clean Cities Coalition stakeholder that has faced the same challenge and will be willing to talk to you about that experience. And that's what we're here for, to connect you with all the right people, other fleets who are having the same issue or have tried out the same technologies that you're interested in trying out, and we can connect you and help you with that. So at Louisiana Clean Fuels, we were established back in 1997, and we received designation as a Clean Cities Coalition in 2000. So this year we're celebrating our 20th anniversary in 2020. Right here it says we're building partnerships to advance affordable domestic transportation and fuel technologies. That is the kind of the Clean Cities motto in a nutshell. As coalitions, we are here to pull people together for a common cause and to work together and to find the right connections for you. So that really is in a nutshell who we are and what we do. And specifically with Louisiana Clean Fuels, this is our territory. We cover about 57 parishes in the state of Louisiana. And we kind of approach our projects in a unique way. It is our simple way. It's the way we look at things is our job to identify, then work to remove all the barriers that prevent both public and private fleets from adopting alternative fuels and advanced technologies into their fleets. And if we can't find something to help you, or if we can't find the answer to your questions, we will find someone who will. So before we hand you off to our panelists today, I wanted to very quickly take a look at our electric vehicle infrastructure. So our favorite tool, or at least my favorite tool on the AFDC, the Alternative Fuel Data Center, is the station locator. This is surprisingly a little well-known, fantastic tool that will let you know exactly where all the alternative fuel stations are. And here I have a snapshot of level 2 electric vehicle charging across our region. And, you know, most of our current electric vehicle charging infrastructure, it does consist of level 2 chargers that have installed at grocery stores, malls, tourist destinations, and workplaces around town. But in order to support interstate travel and larger vehicles with higher energy demands, we need a well-planned out DC fast charging network. So the Federal Highway Administration recently had a program that is continuing on each year where it allows states to designate their interstate corridors as signage ready. So this is a signage program. This is not a program to install chargers, but it is a one to bring awareness of the chargers that are there. And, but first you must meet all the criteria set forth in the plan. For example, in order to get an interstate designated as signage ready for electric vehicles, you must have publicly accessible, universal DC fast chargers placed at a minimum of 50 miles apart, and they must be within 5 miles of the interstate. So again, while this program does not fund fueling station development, it does encourage collaboration among stakeholders along these corridors, and it helps to improve public awareness of alternative fueling in charging sites. And you can see here, Louisiana only has a small segment which is approved as signage ready with the stations that we already have installed and in operation. So the remainder of the I-10 with that dashed line is designated as corridor pending. While there are stations along that corridor, they are not close enough to qualify for signage. So one of the creative things that we did here in Louisiana is, you know, with very little funding, we got really creative with our coalition. Our state got about $19 million in Volkswagen settlement funding. And according to the rules and the guidelines set forth in the Volkswagen settlement, you may only use up to 15% of your money for electric vehicle supply equipment and to install the chargers. That leaves the state of Louisiana approximately $2.85 million for EVSE. So in order to be really strategic about how we spent these limited funds, we had to get a plan. We had to get a game plan together. So we used crowdsourced data, publicly available data sets to conduct our own gap analysis and produced a plan of where to put approximately 13 DC fast chargers along our interstate corridors that would complete all of our major interstate corridors. So we also took this information, not only did we give it to the state and to the lead agency for the DEQ for Volkswagen, we took this information out on the road and we partnered with SWEPCO, CLECO, and Entergy to bring our plan to potential site hosts in the identified locations in order to get them to send in a proposal for the Volkswagen funding. We didn't want to leave it up to chance that the right people would say, yes, we want a DC fast charger on our property, Volkswagen, here is my proposal. We wanted them to be strategically placed so that we could complete the corridors. And you know, the DEQ can't approve what they don't get. So we hit the road and we got some really high quality proposals that were sent in. Now the ink is not dry on any of the third round DC fast charging proposals, but taking a look at what we believe is going to get approved, this is approximately what the Louisiana map will end up looking like. So the yellow and the green would be completed corridors. Now we're hoping that also potentially a station in Monroe would get installed. And if that case, we would have I-20 would be more complete instead of that big red section right there. All right, so in order to take that leap from fast charging corridors for individual interstate travel and commerce to large heavy duty fleets, there's a lot of thoughtful planning and education that needs to occur. So that brings us to why we're here today. This webinar is the first in a 3-part series on transportation electrification for utilities. We're taking you behind the scenes to bring you the latest findings and lessons learned from some of the most exciting pilot projects across the country. First up is Ted Bohn, Principal Engineer for Smart Metering and Electric Vehicle Smart Charging Standards at the Argonne National Lab. Welcome, Ted.
Welcome. Can you hear me?
Yes, I can.
Okay. So I'm going to start. Anne said she was going to take a poll. I recognize about 4 names on the roster, so it's a medium big group, so not so big that we get lost in the details. Like I said, I have a limited amount of time, so I'm just going to dive into it. So again, my name's Ted Bohn at Argonne National Lab. Some of you have met me before. Some of you may have seen the seminar I did in January on what lies ahead. This is considered the 202 level or 201 level, which is you kind of know what big plugs and big vehicles are. We're going to drill into the next level of how big is big and how many is multi-port. Oh, that's you. I'm sorry, Anne, you have to flip it.
Okay.
Next.
The poll is almost done. You'll have a little bit longer in order to finish this poll. There we go. Is that the next one? There we go.
Yep, that is. I am. I'm sorry, my button didn't work because it's not my slides, it's you moving it. So anyway, so today we're going to talk about some recent developments and obstacles, and that's the big thing on how do I, and you're going to see some pictures of like a 1,200 slot truck facility. And it's like every night 1,200 trucks pull in, and you know, in the future, 10 to 100% of them are going to be electric. So medium duty, again, the whole multi-port aspect of it, and some of these trucks are going to require well over a megawatt. So as utility planners, facility planners, people are just coordinating where does the money come from and what do I have to do to charge between 100 kilowatt and a megawatt. So again, 20 kilowatt is good. And Marcy just asked if I'm going to use the camera. No, I'm not. And then we're going to go on to these consequences of managed charging on what some of the peaks are. Next slide.
All right, I just ended the poll. Before I switch to it, we have at 50% are utility, 3% are EV vendors, 21% is nonprofit, 9% government, 3% students, and 15% others. There you go.
Okay, boy, those transitions are slow on the PDF. So going along, a lot of people don't really know what a national lab is or what Argonne National Lab is. So Argonne is the first national lab founded in 1946 as a follow-on to the Manhattan Project in the University of Chicago. So we're still operated by the University of Chicago some 80 years later. Center for Transportation Research is in the upper right. That's in the upper left. That's where my office is. You're going to see a lot of views of the facility in the center at Building 300 in the Interoperability Center, and you can see off to the right are particle accelerators and bioterrorism and chemistry, and the battery lab is just right across the road from this. So we do, materials, computing, nuclear. Next slide. You're going to see a lot of references to the Interoperability Center in some of the lab spaces that I use to do some of the standards development. And again, interoperability means when they plug A into B, it actually works. The smart grid part of it now extends that. So there's a new standard, IEEE P2030.13, which is going to have transmission and distribution requirements for commissioning and configuring the stations as a load to the grid. So the whole idea of grid-friendly operation of these megawatt or multi-megawatt loads, there's a new standard for that that is kind of an extension of the microgrids on the P2030.7.8 and then the P2030.11, which is the DERMS. So if people understand some of these terms, that's where this is headed, from microgrids to DERMS to now transmission distribution impacts on charging station management. In the lower left, you can see the carport with 12 AC charging ports that take the 80 kilowatt AC power above and drop it directly into the vehicle. So from, as we say, from farm to table, from photon to electron to car charging is all of 20 feet. And then in the lower right, you can see some statistics about some of the charge stations. So we have about 50 workplace charging stations spread across the 1,700-acre campus. We have the PV fed arrays you can see here and in 4 other locations. We have DC fast chargers of all sizes, from the smallish, entry-level things you'd see in a service garage at 25 kilowatt to the 50 kilowatt one you see in the center right, the one with the blue label on it, and then to the 200 kilowatt station, which you see to the left, and then the 400 kilowatt station, which looks like that with more power cabinets behind it. Next slide. So this is a different view looking at the charging island, and then there's a plate in the ground that represents where wireless charging pads will be. So this is actually, just to be honest, it's just a plate right now, but that's where if you pull up and did wireless charging, that is one way. I can tie together the other charge stations through the conduits in the building, and that's the idea of the Interoperability Center in the circle in the lower right. I have all these different energy sources that can be connected in parallel up to a megawatt and 1,500 amps at 1,000 volts. So I got a lot of horsepower of things I can do on simulating the grid. In the lower right, you can see some of the equipment that is somewhere between with COVID delays, sitting in a crate, not connected, but soon to be connected or commissioned right now. So in the upper right, you can see the Greco 1 megawatt stationary storage battery. So that's our peak storage. And again, we can do reverse power flow to the grid itself or just behind the meter. That's the whole idea of DERMS. You can see just to the left of that, kind of going around the clock, going around is the dual 400 kilowatt station, the 200 kilowatt station you see here on the left. The blue one, you can, along the blue label, you can see the 50 kilowatt station. You can see some 6 kilowatt AC stations, the billing systems, which again, the building, zero net energy building, because we have all the PV and we have battery systems inside, so we can island the whole facility. So now you can go to the next one. So some of you are on the work group. That's what I call the Megawatt Plus Multi-Port Industry Work Group. It's been going for 2 years now. We have about 300 members in these 4 big groups. And again, since you're utilities, I just thought I would point out a bunch of the utilities are part of this. Anybody, if and when these slides are distributed, you have my contact information. Anybody who's on this call wants to join this group and kind of see firsthand where things are going. We're working as a group on year 1 to define the requirements, on year 2 to look at case studies. We've been looking at that's what most of these slides are from today. And then year 3 is to do a test on interoperability and just develop some of these technologies. And I don't think I'm going to get to the technology side. That'll probably be on part 3 or part 2 of this series, where we talk a little bit more about it on the web meeting next week. So we have the site operators, Electrify America, EVgo, Tesla. We have the EVSE and manufacturers. So again, the people who plan it and use it, the people who build it on the EVSE equipment, the equipment manufacturers, the vehicle side people obviously need to do that. And of course, the next slide. So here's a high-level view, which makes it easier if I had my cursor, but I'll just point out from the right to the left, we have our sub-transmission interconnection. And most of you who are utility people know what that word means, that somehow we bring in power to our substation, and those substations are often capped on what available transmission distribution capacity is at that region. And so in the future, it might be that charging locations are not based on the highway where the trucks are, but based on where the resource is. Again, if it costs an extra $10 million to bring new distribution capacity to a site, you might locate the site closer to the distribution capacity. So going down the blue wires into the white box that said AC to DC conversion. So we have the multi-port aspect of this that has many, where cursor is, takes that AC power and converts it to DC power, can store it with on-site storage, can have a microturbine or reciprocating engine or even a compact nuclear reactor. People have proposed to say, how do I get 20 to 100 megawatt that does not bring down my existing capacity? The same thing with the PV. As the sun gets brighter and goes away in the smoky, foggy days, you will not have that resource, but all the software has to balance all these resources. So that's the takeaway point from this one, is we have some kind of AC coming in. We're going to split it off to between 10 and 600 vehicles. And again, we'll see examples where you don't do that in one big node. You do it in separate connections. Most of you, being utility oriented, know that the low voltage transformer limits are somewhere on the 3,000 to 4,000 amp range, and gets you, about 2.5 megawatt per low voltage transformer, which is why a lot of the work is now going to medium voltage. So we have medium voltage direct solid state transformers from medium voltage to 1,000 volt to 2,000 volt DC. Next slide. So this is what I was just talking about, again, moving from the upper left on this medium voltage connection, somewhere between 13.8 and 138 kV. We have our circuit protection, we have our primary metering, we have the solid state transformer, And again, there's a question mark on the dotted lines about what protocols talk to solid state transformers. We have low voltage DC breakers running again at that 1,000 to 2,000 volt distribution, and then we have the equivalent of a bus bar, and this is called DC as a service, where the utilities would own the equipment, and that line of demarcation isn't where the medium voltage or the low voltage connection is. It's actually at the point here where it says 1,000 volts DC. I keep forgetting, you guys can't see my cursor. In the middle, that's where the energy is sold, and all this equipment upstream of that is owned by the utility. The same with the equipment in the lower right, the on-site battery, photovoltaic, and other site controller might be utility-owned assets that can dispatch according to these protocols that are listed here on the DMP3 OpenADR to best serve the grid and the customer. So basically giving the customer the best price of DC energy, yet managing all the other infrastructure as utility-owned assets. And that's not set yet on how that can happen, but that's what I work a lot on, the metering. So the ANSI C12.32 DC meter standard. There's a whole bunch of pieces have to be in place. It's, again, out of scope what we can talk about in half or 40 minutes. But it is an important obstacle that once it's overcome can open up new markets. And so that whole idea of the ratepayer allocations and the PUCs that can approve selling energy at the DC level directly, that's a big deal. So you can see the open charge point protocol, ISO 15118, which is a communication between the vehicle and these isolated chargers. And so some of you who I know were on the Megawatt Plus meeting, these little bricks, I have a scaled high frequency converter that's about the size of a shoebox. So say, what does that box look like? It could be a shoebox running at 99% conversion efficiency from the utility connection at DC to the vehicle at 99%. So 1% loss means I don't have any maintenance, and that's a huge, huge issue. If you have no filters or other things to maintain, if your efficiency is so high, you have no cooling systems, all you would have is inspection. That's a huge operating cost that you can cut down. That's where we're working on these high efficiency pathways that take the utility-owned distribution node, and again, all NEC and other DC-rated equipment. Just taking the simple math, if I have a 1,200 volt distribution line and a 20 kilowatt, class 4 truck charger is 16 amps, and so that's a 12 gauge wire. So it's like, I get it. 12 gauge wire feeding a shoebox charging my Amazon delivery truck. That's a good future. So I guess we're going to move on to the next slide. This is a Venn diagram that kind of shows the charging process in the middle, but the other things that people have to be aware of. So I always talk about these obstacles, opportunities, failure modes. On the call that happened right before this, the Charn work group was just talking about what happens when people stand on the connector. You plug the connector into the truck and say, look at that. Somebody put a ladder, a handle right here on the side of the truck that I can stand on to go clean my windshield wipers, or clear the snow off. So those failure modes are what are inside this purple circle. So looking at the center, bright yellow dot with the red boundary, we have the charging process, but moving around from the upper left on the utility connection and load management, extremely important, right? We will not have demand charges at 10 megawatt peaks when your average is below 1 megawatt. You'd like to keep your average at 1 megawatt and use whatever it is to keep the customer from paying, thousands up to tens of thousands of dollars per month on demand, because demand may exceed the cost of the energy. To the right, there's DC as a service and the conversion distribution to the electric vehicles that we just covered. Cyber everything. It's very obvious. Anything that's controlled or communicates with a computer interface or some communication link shall be intrinsically sound, not compromised. Mechanized systems. It may be that some of these are heavier or unsafe, again, especially at the megawatt plus level, that a human should not be plugging this into the truck or holding it in the truck. That shall be a automated connection system, i.e. robot. Couplers, cables, cooling systems. Again, we have the ergonomics of OSHA says how much you can actually pick up and plug in. We have these path of egress, all these other issues. And then to the lower left, we have infrastructure planning services, the Black and Beaches and others who say, here's how much panel board you need, here's how much space you need for the conduits, here's where the primary meter goes, here's where the bollards go. So that's a big part of this. Outside the circle are things that are below a megawatt, but still important. In the upper left, we have battery swapping. So clearly a good idea is that like with the forklifts, you have a rack full of batteries that you swap into a vehicle. The vehicle can turn on quickly, and you have the ability to average the offline batteries to a very low rate. In the lower left, we have sub-megawatt charging, and the asterisk is there are people who are doing demonstrations at a megawatt. But the wireless charging system has a price. It's about $1 a watt. So a megawatt wireless charging system is about $1 million installation. In the lower right, we have the sub-megawatt. We're going to talk about that in a second, which is, in general, we have a multi-port system. You don't have to run at a megawatt. You don't have to turn around the truck in 20 minutes. You have 8 hours. So, and then in the upper right, there's the other international standards like Xiaoji, which again has a high voltage but a lower current, and again, it's below a megawatt. Next slide. So we're about a quarter of the way through the material, just to kind of let you know how quickly we're trying to go. There's going to be a lot of installation photos after this, but this one is a little bit intense. And just looking at the row in the middle with all the acronyms, the GBT and the new GBT is that Xiaoji connector, which is what the rest of the world wants to use for heavy-duty vehicles in Asia and likely not Europe. Europe is mainly aligning with Charan and SAE on the MCS connector. So the CCS is a combined charging system, which is backed by Charan and IAC, and most of the world uses this one today, and can deliver 1,000 volts at 500 amps or half a megawatt with liquid cooled cable. The mega charging system is the next tier up, and that one, is a work in progress, and again, a lot of industry. It's basically a industry consortium designing the connector, and then it will be adopted by standard. But the lab prototypes have shown that you can actually run at 3,000 amps and maintain temperature stability. I lead the work group on communication noise immunity, which is, what happens if I put a whole bunch more noise in the connector? Does the system just shut down? Someone should test that. That's what we do in my lab. Okay, next slide. So this is something that a lot of people overlook just because, and looking at the center of the drawing, you can see a circular one with 5 pins next to the Tesla Supercharger connector, and then to the right is the Type 2. So Type 1 Tesla proprietary connector, and then to the right is the Type 1. You can see the difference in the pins. You see a little white dot in the one in the center. That's a 3.7 millimeter pin. The ones on the right appear to be much larger. They are 6 millimeter pins, and so I can run the current a lot higher on this one without going to the combined charging system, which is what you see in the left, in the lower image left side, and that's the Tesla European Supercharger with the CCS to Type 2 adapter. So they run this connector at 120 kilowatt. And again, some people understand power, other people 120 watts, 120 kilowatts. 120 kilowatts is a lot of power. So at 375 volts, that adds up to 320 amps. And if you look at the diagram in the center left with the 2 blue circle, 2 blue ovals, it shows that we can run pairs of pins. And so that's how we get away with running 320 amps on something that's about 50 millimeters across. So again, 2-inch wide connector, 120 kilowatt, and then the bottom bullet says extrapolating to 1,000 volt distribution systems, much like the Lucid Air and some of the other high voltage vehicles. That 320 amps at 1,000 volts makes it 320 kilowatt. And this, again, not a NRTL listed one, but a clone. These connectors can be had for $30. So it's a very low cost way to get a lot of power. And again, looking at the header, I can run this at 208, 277, 480 volt 3-phase, or at the 1,000 volts DC, same connector. So that's a big deal. So anyway, just as far as things you should watch out for, this is a big deal. Next slide. So on to Class 4 vehicles. So this is just kind of a back of the envelope. How much does a Class 4 electric vehicle use? Well, but here's a study with a link from a CalSTAR study done in the early 2000s, published 2018 on the E-Star. And they showed that, running real world delivery things, running a 60 kilowatt hour recharge, they were, miles driven to energy in was about 1,000 watt hours. 1,000 watt hours per mile, kilowatt hour per mile. So the Bollinger Deliver E, which is, Amazon is ordering thousands of these vehicles, literally thousands. This is a typical vehicle with extremely low floor. All the batteries and motors are below this floor, which are below the center of the axle. So you can see it's made for lots of space inside. But just doing the back of the envelope and say, why would I say 20 kilowatt charger? Well, with a 70 kilowatt hour battery, that will give you 70 miles of delivery range. And again, some loops are way less than 70 miles. Others need a lot of repetition between charges and go 200 miles. But even at the 70 miles at 20 kilowatts, that's just over 3 hours of charging. And then again, if I bump that up to 100 kilowatt, that's what we talked about, that's 100 miles per hour of charging. That can be done in just over an hour. So that's back of the envelope on what a Class 4 vehicle needs for charging. Next. When we talk about megawatt level charging, we would say, why do you need 1,000,000 watts? Well, if you just do the math, and again, assuming that the loaded truck with regenerative braking and all the other conservation can manage 2 kilowatt hour per mile. Some people might say that's closer to 4, like a bus is closer to 4 kilowatt hour per mile. But if you can imagine, if you can manage to have 2,000 watt hours of consumption, this is the equivalent of MPG or more, because again, there's hills, there's rain, there's headwinds. But if you had 400 miles of range at 2 kilowatt hour per mile, requires 800 kilowatt hour of usable energy. If I need to turn that around in 30 minutes, which is 2C, that's 1.6 megawatt. That's why we talk about this megawatt plus. There will be times when you want to charge these trucks, and not even metaphorically, literally. These are the principal parties designing this new MCS connector, need that connector yesterday on their vehicle, such that they can turn their customers around in half an hour for 400 miles range, and a half an hour equals 1.6 megawatt plus losses. Shorter routes, again, have trucks that have a lot less capacity, right? So 800 kilowatt hour batteries are on the big side, and again, that's usable. So you have a megawatt hour size battery to use up 80% of that, the 800 kilowatt hour. Some will be over a megawatt hour. Oh, my goodness, that's a megawatt for over an hour to do that, and that's just for one vehicle. You imagine if you have hundreds. Overnight charging might be, you might be able to average that much less, and that's where this whole scheduled charging, managing your peaks. So if you have 8 hours at 100 kilowatt is 800 kilowatt hours. So just simple math. Next. These are the ideas I want to put in your head today. So when we talk about this again next week, it makes more sense after it's had time to absorb. So here's a typical installation. Again, real world electricians on the right. You can see the Tesla power pack, which is again mandatory when you're pushing, you know, in this case, 2 megawatt. And again, we can get 2 megawatt out of one low voltage transformer. So there's a low voltage transformer. You can see the gray cabinet kind of peeking out the back on the left where the panel boards are. So I guess the transformer's back, you know, in the weeds. The Tesla power pack is on the right with the grid-tied inverter and its load center. And then you can see that there are 1, 2, 3, 4, 5, 6 350 kilowatt charging stations. You can see these cabinets, and you can see the green circuit boards, and those are cassettes that are on tracks. And so they're kind of like bricks, right? So there's bricks of power electronics with cooling, and you can see the 480 volt and DC connections in the bottom of the cabinet in the orange and bright yellow. So that's a typical installation. Rows of cabinets, some kind of peak shading, some kind of dispenser, and then of course bollards. Next slide. And this is a big takeaway, and that's what we were just talking about on the previous meeting about safety and robustness and things that aren't quite defined. But the three ways that the connector can get to the vehicle are from the curb, in this case shown from the front, from driving up next to a fuel aisle, which is very much like the way we do liquid fueling now, and then overhead on a gantry structure with, you know, tethered cables that go up to the overhead structure, and then from beneath the flush-mounted pop-up bolts. Next slide. So here's an example of the angle that the cord retriever, so you can see on the right, there's a red arrow that kind of shows that it comes down at an angle and pulls sideways on that cable. So these red, they're called hose saddles, have a counterweight that slide up and down that tube that keep the cable off the ground. And again, you can see the rows of bollards, you can see the peak gravel, you can see the pads, and of course behind the blue fence is the low voltage switchgear. Next. So this one's from the Netherlands. You can see there are 6 pull-through islands, but way in the back where the red rectangle is where the power electronics is. So you can see there's about 100 meters of cable that take the DC power from the AC power conversion and bring it up to the dispensers on the islands. You can see the distance that it goes on the yellow circle on the right that goes from the dispenser to the inlet on the truck. So again, just literally, here's how it's working today. It's going to look a lot like this, except more. And again, these pull-through islands are important. The warehouse to the left is where these trucks operate out of. So this is a charging facility adjacent to the distribution warehouse. Next. So that's what I want to load up these slides with as much as possible on. Here are real-world examples of what the utilities and the fleet operators are you know, looking against. And again, I see more people on the right that I recognize who are literally doing this for a living. So the red rectangles on this canopy, again, one observation is, that's a lot of steel. The next one is, that's even more conduit. And then the third one is, that's a lot of cords that are dangling from the ceiling that go up and down. So the skinny rectangle in the center shows one that is extended, so that you can see there's a kind of a curlicue that looks like the letter I, just the lower right of that triangle, and that's the winch that lets this cable down to plug into the bus. And then of course the triangle or the rectangle to the right shows what these 12 cables look like when they're pulled up. But you can also see, hundreds of feet of cable. And then in the lower left, you can see, for the people who are utility savvy, lots of bollards. They're very skinny bollards, but lots of them protecting the panel boards, the low voltage transformer, and then the green cabinets kind of in the middle there. It's a little fuzzy. Are the power electronics that convert the low voltage AC, the 480 volt three phase, to roughly 600 volt, 500 volt DC at 400 amps. Next slide. So that was an example of the front, above, and this is below. And this is a new area, and I think it's going to be very significant, is when you're plowing a parking lot, you don't want to plow around bollards, especially you're going to see in the next ones are hundreds of truck spots. There's no way you want to plow around anything. You want to plow over it, right? Like at the airport. They don't want to plow around anything. And Murphy says any bollard that's in the middle of the parking lot is going to smash into a trailer. That's what bollards do. They run into trucks, the truck level bucket. So in the lower left, you can see the fuel ports that a lot of people are familiar with at airports. The ground support equipment has prefab tunnels that the fuel lines go from the tank that's someplace else to the fuel truck that pumps it into the wing of the airplane. In the middle left, you can see the air conditioning tubes. Again, there's an air conditioning unit that's over by the edge of the building, goes through a tunnel, and then up into the aircraft. And then in this case, it's a hose, but it represents a large power connector that the person on the right is connecting to the aircraft, and that would be, represent what you would do if a human were connecting. But there might be automated connection systems, such that if the truck is parked in its proper spot, the pop-up can be elevated remotely and can automatically identify the filler door on the truck and fill it. Next slide. So here are two examples of companies I'm working with: a power hydrant and stable. And so the one on the right is a 6-axis. Full-on automation robot, very expensive, lots of maintenance. Some people believe that's just way overkill. On the left is power hydrant. They are actually building 1,000 amp couplers today, and they charge many rows of UPS delivery vehicles. So the idea is that labor is going to be important. Wireless charging is going to be very important, not from the repetitiveness, but the human factors. If a human doesn't have to plug it in, A, that's less labor, and B, that's something that's more guaranteed. Halfway between our automated connection systems, where the truck pulls in, as soon as the person's clear or whatever the signal is, the robot knows it's time to go identify the port through machine vision and insert the connector. In this case, it's like the trunk latch on your car. The connector just gets close and grabs the edge of the connector, the vehicle body, and then it has a motor that drives the two halves together. In case you're wondering how such a lightweight robot can actually push that big bulky connector into the hole, it doesn't. It actually pulls itself into the hole. And of course, when it's done, it pushes itself out and pulls the robot back to the park position. So this one shows a ground-mounted one, which I don't believe is going to be the way it ends up, but that's what's on the website. The ones that run on a track above, I think, are going to be more likely, or ones that are on a wall that reach over. But these are examples of automated connections. Next slide. So again, just state the obvious. If you guys are are people who are planning to say, here are the companies, the ones 1 through 12 are doing business in the United States. The 1 through 5 are people who are kind of doing business, like Siemens builds power supplies, but they don't build connectors. Stemmen makes pantographs, but most trucks won't use pantographs, so that's why they're kind of in that other area. But the ones above are the ones who are part of this Charn consortium and coming up with products to run at this multiples of 100 kilowatt. You can see that most of the cabinets are somewhere between 175 kilowatt and 200 kilowatt per cabinet today. The next generation that I've seen, not released yet, run about 500 kilowatt per cabinet because they're running more advanced electronics, mainly because of maintenance. It's very interesting to hear why maintenance is such a big deal. It's like when you can run higher efficiency and higher power density, you have fewer filters. It wasn't about the cabinet. The cabinet footprint is important, and that's what this table, this is taken from other slides, but basically just said, what is the watts per pound of mass and volume? So gravimetric density, volumetric density, where people are planning this, the big question is, where do I put all this stuff? If those cabinets are the size of a refrigerator for just 175 kilowatt, I'm going to need acres of refrigerators. It just can't be. So that's where the solid state transformers come in, and they can run much higher power density because you're running much higher voltage. Next slide. So I just thought we'd talk a little bit about cable. So on the right, you can see some from Asia where you got 3 guys pulling this fire hose over to the bus and plug it in. So you know this is a stage photo that you don't always need 3 guys to pull a cable, three operators. But here's a case where it's like, that's a lot of cable. And then in the center are AC charging stations. You can see they you know, as always, like the saddle tanks on a truck. If you can't fill it fast enough, you use 2 of them. I see some questions are piling up on the right. I'm going to ask Anne for a time check. Where are we on our budget?
Sorry, I couldn't get to the unmute. It is 11:42. We have 45 minutes remaining for David and for Q&A and for you to wrap up.
So I would say about 15 to 20, I should be done. So I'm on a good pace to finish the next 20 slides. Okay, next slide.
Oops.
So while they're transitioning, so that previous slide was about liquid cooled cables. These are not liquid cooled because you would see heat exchangers on these gray boxes. So this is as literal as it gets. Penske is doing the trial fleet for Freightliner and the E-Cascadia trucks. And you can see the big battery packs on the side. You can see the rubber bumpers that keep the vehicle from, you know, bumping into the bollards, which is just pretty obvious standard layout. And then you can see 6 of these small, I'll call them microwave ovens on a post. So those are the dispensers where the connectors are hung up when they're not used. You can see the hose saddle, the retrievers in the middle, and then the yellow box shows the storage unit. So they're Siemens and I forget which battery company own Fluence, and so Fluency, maybe it's with an E. I probably didn't spell that. Anyway, they build this storage system, and this is going to be an important part. Anywhere there's large charging, there will likely be facility-owned batteries. And again, most of you know that this container isn't cheap. It's like with the one we had at Argonne Lab, it's well over $1 million. You know, like how can a trailer full of batteries be $1 million? Well, that's how much it costs. Plus all the switch gear and other stuff. You can see there's even the HVAC and battery management. And as you've seen in the news, a bunch of these go up in smoke, so it's even worse than spending $1 million. It's $1 million and it burned up, and you have to build another, and you know, $5 million in investigation and other fees on why it burned up. So the battery storage is a really big part of this. But this is an excerpt about their latest one in Ontario, California, which has 6 times 150, which isn't even a megawatt. So I keep talking about this megawatt thing, like even all of these are less than that. My last slide has a method that we can use, a Starline busway, an existing data center power thing that would actually power all these trucks on existing products with existing busways. So it's very interesting when you run a high voltage distribution, how little of copper you can get away with. Next slide. So this is kind of one of my takeaways from today is this that looks like somebody spilled a bunch of toothpicks on the table. Anybody who's driven through California knows in the lower left of this is where you can kind of almost see it where it says the map in that corner. That's the edge of the airport in Ontario. So this is the San Bernardino Freeway, and there's the mall in the upper right, and in the left in that yellow box is TA Petro. They have 600 spots at that location, and you know there's restaurant and showers and stores and all the other stuff that a travel plaza has. And then they also own the TA Petro side, or the Petro Center, something on the right side, and then to the right of that is the truck service. So these truck service plaza industries service, and then to the left of this is that Penske leasing operation. So these fueling and service facilities actually take care of those trucks that are part of the leasing operation. So you can kind of see it's a big cluster. And anybody's been through California, like, well, that's normal. Those are everywhere. There's big, you know, transport centers from the Port of Los Angeles to all the warehouses to City of Industry. It's just, you know, LA sprawls. So next slide. So this is a little bit zoomed in, but the question is, in the lower right where you see the red box, that's the 8 stalls where you have, dual pumps and trucks pull through, they pay for it, and they go park for the night, right? Again, you buy, just taking simple math, 300 gallons of fuel at $4 a gallon, it's $1,200 worth of fuel. You get a parking spot, a good meal, dot, dot, dot. So now for electric charging, what if, and again, the segue to next meeting, we talk about the TRUs, the Transportation Refrigeration Units. For California in 2025, they're mandated to all be zero emission, non-idle. So every one of those reefers that are in this parking lot are supposed to be off after 2025 of all new ones. And so you can see it's like, well, even if you're not charging the vehicle, that is literally hundreds of outlets that have to be deployed across something that's, a very chaotic place. So this is the challenge at hand. How do utilities supply this? What if I say, I would like 10 megawatt tomorrow. Can you just pull that extension cord over here and plug it into my substation, into my load center? I'm like, I don't know, a little bit more planning than that. Again, most people believe that you can get normal service up to, 2.5 megawatt is something I can just go buy. I can just order. But anything above that is going to take more planning. So next, these are some of the takeaway points from today. So other companies are using their PV assets. So there's a company called Power Electronics SA. They have 1.4 megawatt containerized solution that has battery storage, has a whole bunch of charging stations. These could be used for trucks. So again, these things just come on a giant skid with a giant price tag, but they are turnkey. Next. So this kind of gets into the what is ABB and now Hitachi ABB Grids doing. You can see the overhead cable trays, the tan box up in the ceiling is the contactors. From there is the output dispenser that has communication. It goes up, over, down, and then to the side of the vehicle. This takeaway slide talks about their choice was not to have cord retrievers. Because again, if the utility is paying for half or all of the charging installation, maintenance is an issue. In this case, the thin cords are communication and monitoring, and basically just like accessory power for the buses when they're not used. The black cable that's hanging down near the wheel in the lower right is the charging connector. The one on the left is shown plugged into the vehicle on the just above the wheel next to the entrance door. But their philosophy was it is cheaper to replace cords that get torn off by people snagging on the mirrors than it is to replace the cord handlers, which they believe will jam. So there's going to be a lot of trade-offs, but that's a big thing. What is maintenance? Next slide. So this is how ABB, and again, I don't have time to go into the depths, but just suffice it to say the roof of that building has many tons, maybe 100 tons of power supply. So 44 of these, and they're about 4,000 pounds each. They're full of copper. You can see the 4 times 2 MVA transformers that are in the back of the building. You have your medium voltage switchgear, your low voltage switchgear, you have SCADA. It's just, when you go around these labels, there's a lot of stuff, and that's all up on the roof in the mezzanine of this charging station. So this is in Hamburg where they have 44. They're going to go all 1,000 buses. They're going to do that. So this is kind of an analogy towards, look, if there's no room on the ground to mount it, you mount it up in the ceiling, and that building's going to get really expensive when you have that much mass to mount in the ceiling. Next slide. So ABB Grid sold out to Hitachi, and now Hitachi owns 70% share of Hitachi ABB Grid. So again, if you knew them as ABB Grids for the marine and other stuff, it's now Hitachi ABB. This one's a little bit fuzzy because it's pulled from a brochure, but you can see on the right the same medium voltage, low voltage transformers, the cabinet full of power converters, and then the output. So kind of like the synchronous rectification unit, and then you can just see that it has the outputs from 50 kilowatt to 600 kilowatt on different connector, pantograph, or other systems. Next slide. This kind of shows the aggressiveness of Hitachi ABB Grids. In the lower right, you can just see where it says 12 150 kilowatt modules. So that rack has 12 outputs in it. You're like, well, 12 is very small, and I have to do 600. So just doing the math, I need 50 of these shipping containers for that truck facility on just one side of it. So that is a lot. So there are multiplexers that can share multiple units. And again, you can just see that all the services that would go with it on traffic dispatch, infrastructure management, maintenance, energy management, Hitachi ABB Grids is going to dive big on that market. So anybody who is a utility operator or looking at investment their salesman will be happy to drop by and give you a quote on a turnkey, drop this container at your facility and it takes care of it. Okay, so next. So battery energy storage, again, repeated theme. Almost every installation has one of these. Same for Hitachi ABB grids. This is their, and it's not quite a baker's rack, but just racks of storage modules, grid-tied electronics, inverter electronics that manage 1547, islanding, grid forming, right? Very important part. Like this system could be grid forming, and I know David's going to talk about that on microgrids. So it's a very, very important takeaway that this 670 kilowatt hour, 500 kilowatt output storage unit is part of their solution. Next. So this just shows the obvious. If we have, and if this red box in the center represents some kind of power electronic solution, the long skinny red bar is some kind of overhead gantry, and then things that either drop down or come up from. So it could either be buried or go from overhead, but somehow a radial lead goes from the power conversion and storage to the distribution, and it could be that the battery storage is stacked on top of the power electronics, and the power electronics on top of that. So either way, you're going to need some space for a 8 by 20 foot container. These are the DOT guidelines for how you do the angles on how trucks pull in and out. So again, just sighting, just awareness. Here's what it could be or should be. Next. So rounding the corner towards the finish line. Here's how the Tesla Supercharger stations are. And again, these are for for light duty vehicles, not heavy duty vehicles, but the power output at 250 kilowatt per port, is as such. So in Vegas, they have these PV arrays in the upper left. You can see rows of supercharger stations in the middle, which are liquid cooled output cables. And at a fair distance, somewhere between less than 100 and over 100 feet. And then, again, there's long cables. So they have to run multiple 2-watt cables, hundreds of feet to get to that, up to 700 amps peak. So a Tesla Model 3 running at 250 kilowatt runs about 770 amps. These are nameplated much lower than that. So this one shows that the output current of this station is 350 amps at below 35 C, and then 200 amps above 30 C, or up to. I was going to find. 50 C, sorry, so up to 50 C. So anyway, so that's what's inside the dispenser are some cables, and in the lower right, you can see they come up through the ground, they go up along that kind of big red donut. There's some terminal strips you can see in the lower left on how the 2-watt cables terminate onto some flat bus bars. The bus bars go down to parallel conductors that go to the output charging cable for the supercharger. So anybody who hasn't seen the inside, that's what it is. So in the middle of the photo in the upper left, you can see 6 black dots. These are the top of the power converters. Next slide. Those are these power converters. So there are 6 cabinets, and they have 4 outputs each. So on paper, these each put out a megawatt, but the panel board on the left, that big white box, this is the nameplate. You can see it's nameplate rated at 4,000 amps. So, even though it could pull a lot more current from the grid side, it's that. It has PV. I'm not sure if there is storage here, if it can have storage, but the point is that these power converters can share DC power. This is very much so the Tesla version of DC as a service, where they own all the equipment. They have the switchgear connected to, roughly 2.5 MVA grid type connection, but they can supply peak of 250 kilowatt per vehicle. Okay, next. Anyway, like I said, this is very much so what a truck would be. This is what's inside the cabinet. So on the left, some people like circuits, other people that I don't know need to know what's inside. On the top where the mesh is, that's the refrigeration unit that pumps chilled cooling through all the modules on the right. So the top circle are the input, I think there's 70 kVA modules. So this one is I think 5 times 70 kVA, and then the output dispensers, there are 8 modules, roughly 125 kilowatt per module. And then this is the older MCS, predates the MCS coupler, but this is what the installation looks like at Fremont, California, for a dual 250 kilowatt, or basically 2 megawatt peak, installation. So next. So getting on to what we're doing in Argonne Lab, this rounds it out. I see some questions in the box. I'm not sure how we're going to hand that off, but this is what I'm doing. So we've seen in the opening slides, the megawatt level charging stations that I can plug all these together like a big extension cord at 1500 amps at 1000 volts. So that I have the ability to have this motorized platform that I can mount things on to do testing. These are the 5 transmission to vehicle side steps. We have the interconnection, which I'm sure most of you are interested in. We have that low medium voltage conversion to DC, which again is going to take up some space, and so making this as efficient and compact as possible is really important. DC converters for the dispensers. How do I actually split off this power to each of them? The cables, and then of course the vehicle side safety. Next slide. This one's kind of dense, but it kind of shows where we're going. And this is kind of my thought starter for the next one. Is what if I do everything in 20 kilowatt blocks? So I could go on 100 kilowatt, I could go in 2 megawatt. But how if we just start at 20s? So I can make these things the size of a shoebox. So in the lower left is the Fairline busway tap box. And so these tap boxes, if you look at the thing in the center, has this red coated bus bars that go into the slots in the busway. This busway is able to hold 4-pole 400 amp, or basically 800 amps. It's rated at 1000 volts, but I can certainly run at 1200 volts physically, but it's only rated for 1000 as far as the NRTL listing. But the point is, at 1200 volts, 800 amps, I can push a megawatt down this busway. So these are bolted into the building now. I have the ability to in the upper left, to have a bidirectional, again, grid-tied 1200 volt power supply that I can seamlessly put into my control loops on all these these red dots. I can take my communication protocols and plug them right into these off-the-shelf boxes. In the lower left is a Wolf-Speed converter, like I said, runs somewhere around 99%, about the size of a shoebox. If I can have rows of these, I can have between 1 and 50. In the lower center, we have the emulated vehicles. I have physical photovoltaic arrays. I have physical leaf batteries and power conversion. So that's the end of my block, and I will hand it off to David.
Awesome. So David Treichler is the Electric Director of Strategy and Technology at Oncor Electric Delivery, and he's here to share some real-world examples and lessons from the field. Thank you, David, and thank you, Ted.
Thank you, Ann, and everyone who's on the call today, presentation. Can you go to the first slide, Ann? Okay, I put this slide up just because a lot of people are trying to figure out what the whole thing is about electric vehicles that is so different from what it was more than 100 years ago. And a couple of weekends from now, we have the National Drive Electric Week events going on throughout the United States. And Oncor is sponsoring a electric vehicle road rally. And we give out a trophy and some things for people who are doing these road rallies in 5 different cities in and around our service territory. And in looking at that, some of the research I did was the first road rally was in 1894 from Rouen to Paris in France. And they gave out a trophy. And the interesting thing was that the winner of the road rally was a steam car. It wasn't even a gas-powered vehicle. So one of the things that we like to point out is that even among the first road rallies, alternate fuel vehicles were the most effective vehicles even 126 years ago. So I go on to the next slide. Oncor Electric Delivery is in the northern section of Texas. And this map kind of shows the highways that come through our service territory. And one of the things that has caused us to really become involved in the whole electric vehicle, electrification, fleet electrification aspect is the fact that we've determined that about 13% of all freight passes through our service territory. And the primary corridors are I-35 and I-45. I-35 comes up from the Mexican border through San Antonio. I-45 comes up through Houston. And then we have east-west traffic on I-20 and I-30. So we are really a major hub for freight and freight delivery. And anyone who knows anything about the U.S. Automotive industry knows that a lot of the vehicles are assembled in Mexico, but a lot of the components come from Canada and are fabricated up there. So we actually have a lot of traffic where components for automotive manufacturing comes down from Canada, goes to Mexico, goes back to Canada for additional rework, and then comes back down through our service territory to go to Mexico to fabricate the final vehicles. So we have a lot of traffic that moves through here on the Class 6, Class 8 trucks. Another piece of that issue is, for us, is that the Peterbilt company, part of PACCAR, actually fabricates a lot of their Class 8 trucks right in Denton, Texas, which is just north of Dallas. And all of their electric Class 6, Class 8s, and even the Class 4s are going to be built in this Denton facility. So we have a lot of interest locally among companies about the fact that the vehicles are actually going to be built right here. And we have some people who are starting to deploy them as early as next year. Do you want to go to the next slide, Ann? Another part of our analysis in terms of how this affects us with that much freight coming through our service territory is that we've been doing some analysis of where are the logistics center. We've identified that there's 4 pockets of these logistics centers, mostly around the airports and places where the interstate highways cross. So we've actually been able to map out where those specific areas are using a tool that we're going to talk about here in a few minutes. But we have 3 major airports in the area. We have the Dallas-Fort Worth Airport, which is the international airport. We have the Love Field, which is in Dallas itself, but is a landlocked area, so there's not a lot of space for additional logistics in and around that airport. But south of Dallas, there is a place where I-30 and I-20 both cross I-35 and I-45. So we have a lot of the logistics centers there south of that particular airport. And then Ross Perot, who many of you may be familiar with from a previous presidential run a number of years ago, also owned EDS Corporation. His son owns an area around what we call Alliance Airport. It's a private airport that is just used for freight. And there's also a multimodal trains section there as well. So we have a lot of freight that moves through that area, but they're also moving that freight from the air freight and from the rail freight onto trucks. So it's part of the multimodal piece. So we have a lot of electrification discussions that are going on in that particular area. Next slide. So here's just an idea of how closely positioned these particular logistics centers are in our service territory. This is part of the Perot development at Alliance. And one of the things we started realizing, and you can see the airport just above to the right, upper right-hand corner there, where the planes land there. But the thing that got us really focusing in on this was flying into DFW, looking down at all these rooftops of all these logistics centers right next to each other. We started realizing that for us, if companies start electrifying their fleets, a relatively small number of trucks being electrified at any given time because of the proximity of these centers to each other could cause significant overloads at the substations servicing these facilities, because the major facilities themselves, quite often in Dallas-Fort Worth, because we don't have a requirement for heating them or cooling most of them, only have very light electric loads, maybe 100 kilowatts, 150 kilowatts. But if all of a sudden they start electrifying these fleets, as Ted has just shown you, in terms of the electrification power requirements, we're starting to talk about megawatts instantly for each of these facilities, practically overnight, for the first trucks that are coming online. And as I mentioned, Peterbilt and Daimler and the others are going into production for these class 4, 6, 8 trucks next year, 2021. And some of the trucks have already been delivered in California and other places, some of their pre-production trucks. But the actual production lines themselves are slated to go into operation next year. And we have companies in our service territory that have informed us that they are taking delivery of some of these trucks, including the Tesla Semi, which is actually going to be built in Austin shortly after the first of this next year. Will be coming into our service territory, and we'll be looking to try to figure out how to be able to allow them to be charged with our service territory. But for us, a big piece of this, with this close proximity of facilities, is where do we put in additional substations to be able to handle these kinds of loads? As an example, we had one company who came to us, indicated they were looking at building a new logistics center. They have 435 Class 8 tractors. We started looking at how they intended to charge and use those particular tractors. We identified that if they only electrified 10% of their fleet, they required 9 megawatts of power at that facility, which was going to otherwise require 125 kilowatts. If they electrify the entire fleet, 435 trucks, it's going to require 40 megawatts. So we were at that point talking about building a second substation just to be able to service that one building. So these are the kinds of impacts that we're seeing on our transmission and our distribution system in our service territory. And one of the things I'll mention here in a minute, I'll just give you an indication. There are 21,600 fleets in our service territory that we've been able to identify, and we'll talk about that in a minute. You want to go ahead to the next slide, Ann? Here it is, 21,600 fleets in our service territory, and it's a major issue for us in terms of how do we get to all those fleets, because as an electric utility, our key account managers don't start talking to somebody until they have a megawatt of load. So all of our fleets have 100 kilowatts for the most part. A few of the people who have specialization warehousing logistics centers have more than that and have a key account managers. But when I started talking to our C&I commercial industrial manager or key account managers, he said, sounds like I need to go hire some more people here soon. And with 21,000 fleets, it sounds like that's probably a good assumption. Next slide. So this tool we talked about, what we decided as we started looking at this whole issue was 21,600 fleets. We have all these logistics centers. We know we have a problem here. How are we going to be able to address it, particularly when we have to start looking at, in some cases, 2 to 3 years to get a substation built, particularly if we're talking about land acquisition in areas where there's not a lot of available land in these congregated logistics centers. So we had just a couple of years ago built a strategic growth tool, which allowed us to identify the current capacity and available capacity of the substations throughout our service territory. And that was the first thing we put into this tool. The second thing we did was we then went out to the state demographer and started looking at the growth forecasts for our service territory by zip code and started layering in the growth out for the next 20 years based on demographer's data. It actually goes out 30 years to 2050 now. So we started working that into it. Then we started looking at how do we build in things like where new highways are being built, put that into the system. Got some information from the state water forecasting people in terms of where water loads are expected to grow, what are the data that they're using for that. So we found was no one had a really good single forecast of growth for our service territory. So we built algorithms around multi-sources of data of forecasted growth. And from what we're seeing from a number of factors around the country is that even the state demographer's growth levels appear to be somewhat pessimistic because people who are experiencing severe weather issues are starting to look at moving operations and moving people to our service territory because we're relatively isolated from most of those. And we do a lot of work in terms of supporting the hurricanes and things that come along the Gulf Coast. Currently, Oncor has some of our transmission crews out restoring or rebuilding the transmission lines over in the energy service territory in Louisiana as a result of the last hurricane that came through. And part of that is selfish because we're a Sempra company, which owns San Diego Gas and Electric and Southern California Gas. They also own the Cameron LNG facility where they liquefy natural gas, which is on the Louisiana coast. And they have been out of operation since the last hurricane came through because Entergy's transmission lines went down. So we got a call from our folks saying, can you go help Entergy get their lines back up quickly because we want to get Cameron back online. So this is our beginning parts of our tool. We'll talk some more about it. Go on to the next slide, Ann. So we identified from our Council of Governments and the Clean Cities folks here in the Dallas-Fort Worth area, a layer of information that we could put into our tool that identifies every building of 80,000 square feet or larger throughout our service territory. So we use that to try to identify where are these logistics centers, how big are they, and so on. Next slide, please. We obtained from a company called FleetSeek data on the 21,600 fleets that we have. Part of the issue we have in terms of data is that FleetSeek has the information based on where is the location where the trucks are registered. In most cases, that's the headquarters or the regional operations center for that particular fleet operator. So we know who owns the fleet. We have a contact by name, a person. We can contact their telephone number, their address, but we don't know exactly where those fleets are located in terms of which trucks are where. But we now have a contact where we can actually go start assigning those out. But we have been building some algorithms based on the square footage, the types of operations, where we're building some estimates into the tool. So we're starting to be able to use that for our planning purposes to try to start identifying where do we think are the companies that are most likely to electrify housing their fleets and what kind of vehicles are likely to be there and what kind of operational requirements do we think that they have. and then start doing some initial planning about where do we need to start identifying parcels to build new substations, where are our current conductors probably undersized for the kinds of loads that we're going to have to be serving, and things of this nature, so we can start looking at the impacts on our CapEx budgets. Because we've already had a number of companies that we know are taking delivery of small numbers of vehicles in 2021. We believe that for the most part so far, that for those we have done the analysis for them, that we can handle those initial vehicles in the 2021-2022 era. But starting in 2023, we may end up starting to see ourselves with some significant issues of not having enough time to get the capacity in place, particularly if some people who today have not expressed interest do in fact come forward and say that they're going to move forward with us. Next slide, please. We also obtained information from the Texas Department of Education about the addresses of all of our school bus garages by school district. And in Texas, I can't tell you about other states, but in Texas, we are able to obtain from them the fleet composition and age. So we actually know what manufacturer or buses are there and what year they are and whether they're diesel or whether it's CNG or what's their current power requirements. Next slide. And Ted made reference to microgrids. One of the things that we're starting to try to build into our tool and starting to look at as a part of our discussions with our various customers who are looking to electrify their fleets is how do we address resiliency, particularly for these larger companies. And what we're finding is that the first companies that are going forward with electrifying their fleets tend to be companies that are participating in what's referred on Wall Street as ESG, which is environmental, social, and governance criteria. And I was on a webinar yesterday where some folks were saying that by 2030, they think that 50% of all publicly listed companies will probably be reporting ESG attainment levels. So some of the companies we're seeing right now that are talking to us are those who are trying to get ready to make their first environmental reports into their annual reports this next year and are setting aggressive goals to start electrifying their fleets right now. But as part of that, since as they electrify more and more of their fleets, they're looking for how are they going to be able to ensure 24-hour, 7-day-a-week operations for these fleets, particularly when you have bad weather that periodically comes through. So resiliency becomes a piece of that. Ted spoke specifically about battery being a piece of what we're seeing. We're seeing at the DFW airport, they're looking at alternative ways to ensure that they have the ability to charge electric buses and things that they're bringing onto their site. So they're looking at bringing in some second life batteries as a way of potentially ensuring they have the ability to charge if there is any kind of an outage. Even though at that particular airport, we have 3 different transmission lines serving our airport coming from different directions. So the probability of outage there is very, very small, but they're still looking at ways to make sure that they don't even have any kind of on-site issues that could put them out given the resiliency redundancy that we have. But microgrids is one of the things that we've looked at. This particular microgrid that Oncor operates in Lancaster, Texas, which is 20 miles south of Dallas, has been in operation for over 5 years. The middle battery you see there was number 4 battery off the Tesla stationary storage line in Fremont that went in 2013. It was only the second one that did not go into power a Tesla facility nationwide. That battery system has since been replaced with a newer model, but we've been gathering the data, learning the lessons, using solar, propane gas turbine generators, and different solar orientation, so we can check the time of day charging, things of this. This particular site where we have this is our central shop for our transformers. So where we have any kind of an outage anywhere in our system, the outages are the transformers are picked up at this site and run out to the location. When we've had hurricane issues in Houston, we actually have a mobile substation that we can move from this site down to Houston. And we have on multiple occasions taken that substation down there from here. So this is a 24-hour, 7-day-a-week operation site. So we've had a microgrid in operation there for the last 5 years just to be able to address that. But we've had the ability to learn lessons here, how we can support our fleet operators who are also looking to try to figure out how to put in significant redundancy to ensure that they don't run into an operational issue. Next slide. So the tool will permit our planners to identify the issues up front. We're adding people to our team to be able to go out and start working with the 21,600 fleet owners in our service territory, just to start advising them of what is the process if they decide to start electrifying, and to also, when they start identifying needs, to work that through our system. We've been doing a lot of Six Sigma projects around how to improve our transaction flow so that we can get information to our customers quicker and actually be able to bring them online with capacity much faster than we have historically, just to be able to make sure that anybody who decides to start electrifying a fleet will not point to the utility and say, well, we were unable to put our trucks in service because the utility wasn't able to get our service to us quickly enough. Next slide. So again, we've actually already been able, through our improvements, been able to reduce the amount of time for initial analysis from a couple of weeks down to 24 hours. And we hope to be able to get to the point where we can give customers using our tool some online feedback while we're actually talking to them on the phone the first time they call in about what are the issues that Oncor might have in terms of being able to service their initial needs, but also what the issues might be longer term. And we're working with our utility commission in the state of Texas right now to talk to them about giving us some flexibility around early investments that we make to be able to address the fleet owners who transition out their fleets over multiple years. People with the Penske Rider type fleets, in many cases, change out 10, 15, 20% of their fleets every year to keep them refreshed. For people who are doing that and are transitioning to electric, we want to make sure that we have sufficient capacity within that 3, 5, 10-year time frame to have the ability to keep capacity in place and keep resilient and reliable power available to them. Next slide, which I think is the last one. Yeah, this is just information from us that we tell the people about who to contact. At Oncor, I'm known as the EV Sherpa, because my role is to carry the load for them within our organization so they don't have to. Anybody who calls me, I get to the right people and get the information to them as soon as I receive it from the customer. And by the end of the year, our tool will be complete, and then we'll have people who will be out proactively calling on all these other fleet owners to start identifying what their needs are, make sure they understand our process, what it takes for us to get it done, so that we can work together to make sure that they never have a day of outage that precludes them from serving their customers' needs. That's my presentation.
Awesome. Thank you so much, David. All right, so now we have about 10 minutes for some questions and answers. If you have any questions that you would like to ask, please type them into the Q&A box in the toolbar that you will see probably at the bottom of your screen. Just move your mouse down there and it should appear. All right, so we only have one question that is still left unanswered. This is from Jeff. He said, is anyone looking at putting the large battery packs in the trailers? This would allow level 2 charging while the trailer is dropped, unloaded, and reloaded. The truck could just attach to another trailer containing charged batteries and could be off down the road. So either one of you want to take a stab at this question?
This is Ted. That was a two-part one. The other part of it gave clarification, and I answered that with a whole bunch of links. So there's about 10 companies tried it. None of them have done it financially successful just because the cost of the trailers is very low. And so it's hard to be competitive. But it's been tried, and but nobody's done it successfully. And again, just going back, like I said, I could spend a whole hour on powertrain design for the trucks, and the operating cost is I think the main thing. So the charging, I didn't really get a chance to talk about this whole opportunity between the class 4 trucks, because again, a lot of people always think about when they hear truck, they think class 8, but there's many different missions. So for instance, snack trucks haul mostly air with some plastic and then some potato chips in between the plastic and air. But the beverage trucks, they run it at GVW. So those would be the kind of the two ends of, sometimes I'm hauling something very light, sometimes I'm hauling very heavy, and that all has to do with the GVW rating. You get the 80,000 pound weight limit on the interstate system. So anything you put onto the trailer takes away from that capacity. It has to give more benefit than the capacity given up. So that's usually the biggest challenge. So that's where the trucks that are pushing a megawatt hour in the semi and reducing their operating costs, as Dave was just saying, it's not a matter of if, but when. And then, I see some people from Southern Company. They have customers who are asking real questions on how do I get ready? So I think that's the biggest thing. But it is a good question to say, can I use lower power charging over more hours when the truck is out of service, and then couple it up? And that's what we're working on with these automated connection systems, wireless charging, DC charging. I'm mainly focusing on how do I distribute large amounts of power to many ports. So I can have one converter that serves, say, 20 trucks, or if I can have one robot that reaches through and plugs in 4 trucks every night. That would be a savings. Rather than one robot per truck, I can have 4 per truck. And that's where people are really trying to cut out the human thing, much like pallet stacking equipment. It's one thing to have a person whose job is to take it off the conveyor belt, put it onto a pallet, but that's not how things work. You don't have, unless you're doing job creation, you don't have a person whose job is to walk around the parking lot, plugging and unplugging trucks. You have a machine to do that because it can be more repetitive and again, sometimes with safety and electrical faults. Anyway, I don't see any other questions. So Ann, did you have I can see the one with David is.
Yeah, I see the questions from Dave Schaller, so I'll give him a plug, because from our experience, the North American Council for Freight Efficiency is probably the organization that has the most specific data that the fleet owners need. And in fact, we're in the process of trying to link our particular EV website into their website, because we think it is probably the most comprehensive site for information for the fleet owners to use. We do belong to SEPA, and we participate in all of their efforts. EEI and EPRI and others all have active things that are going on that are helpful. But if there's one source that I would suggest someone go look at their material, it's the North American Council for Freight Efficiency. They have by far done the best job of providing the information that the fleet owner needs to have in order to make decisions about what they're going to do. Now, one of the things I'd just add in here is, because Ted reminded me of it, we're working right now with one of our local companies that's intending to put 10 Class 8 trucks into service, but they're going to be running those Class 8 trucks 24/7. So their charging requirements are going to be a little extreme. They're looking for 10 trucks, they're looking for 3.5 megawatts of charging power. Each of the chargers that they will be putting in place are 750 kilowatts each port, and they're only talking 2 chargers. So with two ports on a charger, all at one location. And this is okay. We're talking 3.5 megawatts of power for 10 trucks. They're operating 24 hours a day. So one of the key factors here that we have to be aware of is that different companies are going to use these trucks differently. The companies that are doing their local delivery, those are going to be overnight charging, and we've got one overnight delivery company that's already come to us with 2 sites with 1,500 trucks that they're going to be operating out of each of those sites, and they're going to be running all day long, but they don't deliver at night currently. So their plan is to use 25 kilowatt DC fast chargers, which are much slower than these big ones, but still that requires a significant amount of power to be able to charge those trucks. So the operational requirements of the company is what's going to really drive their power profiles, if you will, or load shapes. But the thing that everyone has to keep in mind is that companies' requirements change over time as their customers change. And the pandemic is a classic example of it. If all the trucks out there that Amazon was using today were all electric, they would not have been able to respond to step up their deliveries without using internal combustion engine vehicles to augment their operations. We couldn't have done it because we could not have added additional capacity fast enough for them to be able to amp up what they've done. So all the companies we're talking to are all looking at the current pandemic and saying, this is an issue. We have to have some flexibility. We can't go to an optimized charging profile, even though we will use that most of the time. We're going to need additional capacity to be able to address changes in customers, changes in our operational requirements. So in most cases, we're going to find ourselves building out capacity that's in excess of what their actual needs are on a daily basis. But if we optimize them and try to go there, and this is part of our discussion with our commission, if we try to go to optimize loads, the customers are going to be out of business, or they're going to have a secondary fleet of internal combustion engine vehicles just to keep their operations going.
And I'll add in the keyword Oh, I was going to add on the keyword of margin, that everyone thinks that they can run with zero margin. You have to have between 20 and 50%. So the one ironic thing I was going to add, and I'm sorry to cut you offhand, was the ironic thing is on Amazon, the brick and mortar buildings that they put out of business all have great distribution capability that's unused. So where they're parking the trailers at the closed down mall also has, you know, some capacity. Anyway, it's the whole of repurposing things that are no longer needed. That's one opportunity, but it doesn't exist everywhere. There's always not free unused space. So go ahead, Ann, I'm sorry.
Dave Schaller has a clarification. He says, thank you very much for the kind words on NACFE, but they wanted to learn from some of the utilities. So are there any utilities out there that y'all are finding are just super, super helpful or really on the ball that he could start leaning on for projects, for information and assistance?
My experience, and I think that Ted's seen this too from his work, Southern California Edison probably has the most aggressive programs out there now for fleets. They've gotten special permission from the state of California's commission to be able to do some medium and heavy duty pilot projects, and they're doing quite a bit of things there now to actually support the company owners to do these pilots and get them in place. They probably have done more projects than anybody else, although Lincoln Wood and the folks over at Southern are starting to do more things over there. My friends, my kissing cousins, if you will, at Sempra and San Diego Gas and Electric are doing quite a few things there as well. But if there was a leader around the country in terms of most projects completed, and that's primarily because of the stuff that's going on at the Long Beach port, it's probably Southern California Edison. And Katie Sloan, who's the woman who runs their operations, is extremely knowledgeable, very helpful, and she's willing to learn for everybody. She came over and actually had a whole team of her people look at our tool because they didn't have anything like it when we started building it. And we share that kind of information with everybody. We all try to work together, try to be as helpful as we can in helping everybody get prepared for this.
All right, so we have time for this one last question. John asked, is a modular battery exchange system swap feasible for trailers or engine systems to allow charges for use and time to load batteries?
Yeah, and this is Ted. I'll just take that one as a segue to next week's thing. And I see Fernando's on the line, and David. We're going to have more talk about how do we divide and conquer. But the battery swap not in the United States, because it turns out one battery system for a vehicle is really expensive. As 350 Green and Project Better Place found out, 3 battery systems per vehicle, super expensive. So that's what you have to have when you do battery swapping, is you don't just have to have one per vehicle, you have to have 3, one on charge, one that's ready to go into the vehicle, and one that's on the road. So that's why people aren't doing battery swapping here. But in China and other places where they have more people and space, that is an option. But it is 99% sure not going to happen here because of economics. And as Dave was just saying, in Texas, there's people who are not going to even stop long enough to swap. So it's an idea, but it's not. It's like I said, history has shown that it's not going to happen, especially with Project Better Place going through almost $1 billion with a B dollars before they realize they cannot get their money back. And the same with Tesla, showing that only to get the carbon credits in California, but to never actually use it because the cost of that extra infrastructure does not pay the difference. So.
Thank you so much. So Ted and David, it's been fantastic. We gave us a lot to think about, and we are going to continue this conversation next week with part 2. And we have Dave Schaller is going to be the moderator next week from NACFE, and we have Fernando with HDR who will be speaking again with Ted. So we have a great lineup for you next week. And a little bit out of order, our part 3 used to be our part 1, but it got canceled due to Hurricane Laura. So our first webinar, which was designed to be an intro for utilities to give you some basic information and get you up to speed on all the jargon and lingo and information about electric charging, that is actually our last webinar, and it will be on September 30th. And we will send you all the links to register if you are not already registered. And we also want to tell you about our next webinar series to continue this conversation. This is for fleet electrification. So if you want to learn a little bit more about the vehicles that are coming from Daimler and from Volvo, we've got fantastic speakers who are going to give you the inside scoop on everything that's happening with the pilot projects and the demonstrations. And then we're going to go into fleet electrification tips. So what do you need to know? What are the first steps? What are the different considerations? So we're taking it back a little bit, getting a little bit back to basics, and helping you get started with your conversions. So that would be it for our webinar today. I wanted to thank our partners once again with Dallas-Fort Worth and Land of Enchantment and Arkansas. Thank you so much for helping us to promote this webinar. And we look forward to seeing you all here again next week on our Webinar Wednesday. Thank you very much, everyone.